Welcome back to the third part of the second week. Here we are going to revisit our greedy approach for the generic optimization problem that we set up in the first part. And we are going to argue that if the family that was handed to us was in fact a matroid over the universe that it was defined on, then the greedy algorithm is actually going to work out. So I'm going to recap the setup for you in a moment, but before that we just need one more piece of terminology around matroids. So recall that a matroid is a family over a universe U which satisfies these three properties we said was non-emptiness, heredity, and the exchange property. And to just recap these really quick, non-emptiness simply said that the empty set belongs to the family F. Heredity said that if X is an F and Y is a subset of X, then Y must also belong to F. And the exchange property said that if X, Y belong to F, and if X is a bigger set than Y, not necessarily a superset, but just a bigger set, then there exists some element in X minus Y such that Y union X also belongs to the family F. Okay. So I just want to introduce some terminology that's common around matroids so that when you're working with them, all of this will be pretty familiar to you. So the first concept is that of an independent set. And this one can be a little bit confusing because you may have seen independent sets in graphs, and those are a little bit different. In fact, the collection of independent sets in a graph actually does not form a matroid because you can actually experience a violation of the exchange property again. It's very similar to the matchings example that we saw. So watch out for that. But the terminology independent set is actually used for all the elements of the family associated with a matroid, right? So if you have, let's say, these linearly independent columns, those are called independent sets. The forests that we saw, those would be called independent sets in the context of the matroid that they belong to. And this is again a hangover from linear algebra terminology because, well, the linear matroid does consist of linearly independent columns, so the independence term was kind of inspired from there. So all elements of the family are called independent sets, and any maximal element in F are called basis elements. Okay, so so basically, what is a maximal element? It's an element which is not strictly contained in anything else. So I'm using the word element in the sense of an element of the family, so that's actually a set. Okay, so a set in the family F is maximal if there is no other set that contains it. In some sense, you cannot extend it any further. Okay, so that's what we mean by maximal. And if a set is maximal, then it's called a basis. We claim that all bases, all sets that qualify as a basis actually have the same size. So let's quickly argue this. If X and Y belong to the family F, and if X and Y are basis elements, which is to say that X and Y are maximal in F, then X and Y have the same size. Okay, and this follows actually from a combination of the exchange property, and we'll see if we also need to invoke heredity. So we have X and we have y, and for the sake of contradiction, suppose this is not true. Okay, suppose x and y don't have the same size, then, well, either x is bigger than y or y is bigger than x. Let's just assume that x is bigger than y, so y is now a smaller set. Now, what does the exchange property tell us? Well, of course, y could be again anywhere with respect to x, fully disjoint, slightly overlapping, or fully inside. But what we know for sure is that by the exchange property, we can take something in x minus y, add it to y, and this y union x would also belong to our family F. That's what's guaranteed by the exchange axiom, which we can invoke here. So I'm going to use this symbol to denote a contradiction. So what's the contradiction? The contradiction is that we have found a set which contains y and is also independent, meaning that it belongs to F, right? But y was supposedly maximal, which means that there shouldn't be any other set that contains it and belongs to F, right? So that is our contradiction. Therefore, x cannot be bigger than y, and by the same argument, y cannot be bigger than x, because if y is bigger than x, you would have found something in y minus x that you could add to x, and that would contradict the maximality of x, right? Therefore, x and y must have the same size, and in fact, we did not need to explicitly use heredity here. The exchange axiom was enough to see this proof home, right? So all basis elements have the same size, and this common size of all the basis elements is called the rank of the matroid. Okay, so our optimization problem basically tries to find a basis element that has the largest weight. If you think of it in terms of the examples that we have seen before, well, for instance, as far as a connected graph is concerned, if you look at the graphic matroid associated with that, then the basis elements would basically form a spanning tree, because as long as you only have a forest, that means that you can still add more things to it and still remain independent, still be in the family. So the basis elements would correspond to the spanning trees, and all of them will have the same rank, which is n minus 1 if you're working with a connected graph on n vertices. So that's just a quick example of all of this terminology in action. And I should also mention that if you have a set which is not in the family, sometimes it's called a dependent set, which is just the opposite of independent. So that's something that's worth remembering. If you're in the family, then you're an independent set. If you're out of the family, then you're a dependent set. And there's also a lot of further terminology that's associated with dependent sets, and just like we have maximal independent sets, we also have minimal dependent sets, and those are called circuits. But most of our discussion will not really require us to be working with circuits or dependent sets, so I'm going to not get into that terminology explicitly here. What's useful is to remember that members of F are called independent. The maximal elements in F, the maximal sets in F, all have the same size. That common size is called the rank. So rank, independent, these are the two words that are worth remembering from this discussion. Now let's get back to the greedy algorithm, and once again remember that the input is u and f, a weight function from u to, let's say, non-negative rationals, and oracle axis to f. This is the input, and the output that we are looking for is a max weight set in f. That's what we are trying to find. So that's our setting. Alright, so now let's talk about the greedy algorithm that we have. So following the terminology that we will be using in the notes, I'm going to call this the greedy basis algorithm that takes U and F as input. And what we're going to do is sort the elements of the universe in decreasing order of weight. So that's the first step. We are going to pull up the heavier elements first, the lighter elements come at the end. And our solution is going to be initialized to an empty set. So I think we used X previously to denote the solution, so I'll continue to do that. And this time, let's say that this order that we have picked is, it's just going from 1 to n. So in particular, what I mean is, if I talk about EI by this renaming, EI is going to be the ith heaviest element in the collection. Okay, so this way I can define my for loop nicely. So I'm going to say for I in 1 to n. And remember, the if condition was just that if X union EI belongs to F, then we are going to say X is X union EI. And at the end, all we do is return X. And that's the greedy procedure right here. And once again, let me remind you that it's in this line here that we are invoking the oracle access to figure out if we can add the current element to the solution that we have built so far. Does it maintain independence or not? That's the part in the algorithm where we actually have to use the oracle. And the algorithm itself, like most greedy algorithms, is very simple. It just runs through the elements one by one, starting with the heaviest elements first, and it includes an element in the current solution whenever it can, and if it can't, it just moves on to the next element. That's all that this algorithm is doing. And we saw that if we just try to apply this on an arbitrary family, then this may not work. But now we are going to assume that our family here does have the matroid structure, and let's see how that's going to help us. Okay, so once again, we are going to be comparing the output of the greedy algorithm, and let's say that output is F1, F2, and so on up to Fk, just as before. And let's say opt is G1, G2 up to Gk. So notice that we can actually now assume that the output of the greedy algorithm and the optimal solution actually have the same number of elements, and that number is actually equal to the rank of the matroid. So K is in fact the rank, and let's just spend a minute convincing ourselves that this is in fact the case. So of course, K cannot be more than the rank, because by design, greedy always outputs something in F, and we have just seen that all the maximal sets in F have size equal to the rank, right? So the family F cannot have sets whose sizes are bigger than the rank of the matroid, because that just violates the definition. And since greedy by design always outputs something in the family, the number of elements it has is at most the rank. Similarly, the optimal solution also is constrained to only output sets from F. So as far as opt is concerned, it can also not output more elements than the value of the rank. Notice that opt will not fall short of the rank because all our weights are non-negative. So if the optimal solution had fewer elements than the rank of the matroid, then it can always pursue maximality. So for example, let's say that opt outputs some set S where the size of the set is strictly less than the rank, that means that there is some T that actually contains S. S is not maximal, and the value of T in terms of its weight is going to be at least the value of S, because all of our weights are non-negative. So greedy can simply move from S to T, and it can keep doing this till it gets stuck without hurting its cost. So without loss of generality, we can always assume that the size of the set that's output by the optimum algorithm is actually equal to the rank. Okay, so that's I think straightforward to see. On the other hand, why will the greedy algorithm also pick up rank many elements, right? Let's think about that for a second. Suppose the greedy algorithm runs its course and it ends up with some set S where the size of set S is less than the rank of the matroid. This again means that there is some T which is a superset of S, and T is in the family F, right? So now let's look at this T, and let's look at an element E which is in T but which is not in S. When greedy was processing the elements, at some point it must have encountered the element E, and up to this point it had picked up some elements which I'm going to denote by S prime. Notice that S prime is a subset of S, yes, and S prime union E is also a part of the family F by heredity, right? Because S prime is sitting inside S, E and S prime are both sitting inside T, so S prime union E must be in the family F by the hereditary property of the family, right? Therefore, when greedy reached this stage, it had no reason to ignore E, because by adding E to whatever it has picked up so far, it would still maintain independence. So there was no harm in picking up E, and so we have a violation of the behavior of greedy if our final output does not have rank many elements in it. Okay, so both greedy and opt actually produce sets of size k where k is the rank of the matroid. So we can work with that to begin with. And as we were trying to do before, let's try and compare the outcome of the greedy choices with the optimal ones. And let's actually ask ourselves, what about F1 versus G1, which is the heavier element? Let's say F1 turns out to be the heavier one, and this goes on for a while. But as we said before, there must be some point where this stops happening, because if this is what happens till the end, then the greedy outcome is certainly as good as the optimum outcome. So let's say that this breaks down here, and P is the first time that the greedy choice falls short of the optimum choice. So greedy picks up something that is not as heavy as the corresponding element in the optimal algorithm. So let's think about why greedy was forced to make this choice. So up to here we are doing well, and when it came to the pth element, somehow greedy made a choice which was not as good as opt. Okay, so now let's focus on these two sets here, G1 through GP and F1 through FP minus 1. Okay, so on the greedy side, we go up to the previous iteration from the iteration where we fell short of opt for the first time, and in opt we go all the way to the pth element that was chosen by opt. Okay, by the way, I did not perhaps make it explicit, but I'm going to order both opt and the greedy elements in decreasing order of weight, or at least non-increasing order of weight, which means that the way these elements are lined up is that F1 is the heaviest element among all the FIs, and G1 is the heaviest element among all the GIs, and so on and so forth. Okay, so sorry if I wasn't explicit about that in the beginning, but that's how these elements are organized, right? Now pause here for a second and think about what property of the matroid could we actually invoke here to get our final contradiction. Notice that this set here is bigger than this one here. So let me call this set X, and let me call this set Y, the two highlighted sets. So just to be clear, X is G1, G2 up to GP, and Y is F1, F2 up to FP minus 1. Okay, now we have that X is bigger than Y, and this should ring a bell because this is the prerequisite that we have for the exchange property. And of course, notice that X and Y are both sets in F because, well, X is a subset of the final optimal output. So the optimal outcome sits in F, and by heredity, any subset is also in F. So X is in F, and that's the same for Y as well. Y is in fact being built up in such a way by the greedy algorithm that we know that at every stage we have something from F. So Y belongs to F just by the mechanics of the greedy algorithm, right? So X and Y are both sets in F, and X is a bigger set, which means that there is some element sitting inside X which is not in Y, meaning there must be something here which was not picked up by greedy, but which is actually heavier than FP. Why is it heavier than FP? Because GP is heavier than FP by assumption, and so all the elements that come before GP are also at least as heavy as GP. So whatever element we have in X minus Y, right, which is guaranteed to us by the exchange axiom. So remember, what we know is that there is some X in X minus Y such that Y union X is in F, right? And notice that whatever that element is, let's say it's some GI, right? That GI must have been heavier when compared to FP, which means that greedy had encountered GI before it came to FP, because greedy is processing elements in decreasing order of weight or non-increasing order of weight, right? So GI must have shown up earlier, and because GI is in X minus Y, it means that greedy chose to not pick up GI, right? But why would it not pick up GI? Because Y union GI is actually in F, which means that at whatever stage greedy was when GI came up for consideration, that is some subset of Y, and that subset union GI is also in F because the bigger set, again, this is by heredity, right? So it is flawed for greedy to not have picked up GI at that point of time. It's a miss. It violates the greedy behavior, right? So that's our contradiction basically, right? And notice that the exchange property helped us pull out this element which would drive the contradiction. Without the exchange property, without that structure in the family, we would not have been able to prove the correctness the way we just did. Okay, so that assures us that greedy is in fact guaranteed to work, and that's pretty much the entire proof right here, and I hope that it was convincing. What we are going to see next is, in some sense, contrasting theorem, which basically says that if you're working with some family which is not a matroid, then I can always adversarially come up with a weighting scheme which will make greedy fail. So in some sense, this is the best that we can hope for. If you don't have the matroid property, then greedy is in fact not guaranteed to work in some sense. So we'll come back and discuss that in the next video, and after that we will go on to talk about the problem of scheduling with deadlines, which is a problem that we'll set up, and we will argue that it has this matroid structure, so we can just blindly say that greedy will work without having to prove explicitly that greedy works. Okay, so that's pretty much all I have for this part. I will see you in the next video. Thank you.